Welcome to the AI Vector Search What's New and What's Next session. My name is Maria Colgan, and joining me today is Tirthankar Lahiri, Senior Vice President of AI Engines and Mission Critical Transactions in the Oracle database. Over to you, Tirthankar.
Thank you, Maria. So this is, what databases have always been good at in the past. They've been fantastic at searching for data by values. This is what databases have historically always excelled at, like finding top products by revenue, for example. Now, there is a growing need to extend this basic capability by being able to search all kinds of data, structured and unstructured data, not just by values, but by their semantic similarity. For instance, finding the top 10 products that match a photo or a text description in terms of similarity. This is now made possible by a new breakthrough technology known as AI vector search. AI vector search enables searching a variety of data types, such as documents, images, as well as structured data and unstructured data, based on the semantic contents of the data, rather than the actual values like words or pixels. The way this works is AI vector search represents the semantic content of data, such as, again, documents, videos, images, or even relational data, as a sequence of numbers called a vector. Developers can create vectors for a given piece of data by invoking their chosen deep learning model, also known as an embedding model. And these are black magic entities that basically convert very sophisticated data into this list of numbers. And once this list has been created, known as a vector, this vector can then be stored natively in the database and be compared with other vectors to find objects with similar semantic content. Now, once you create the vectors, there's not very much interesting you can do with them, apart from finding out what the mathematical distance between them is. And there are many different mathematical distance formula. One example is Euclidean squared, which just takes the sum of the squares of the difference of each number. It's a very simple formula used widely also for vector distance calculations. Now, this is where vectors really enable similarity search because they obey the similarity property. Vector distance between two vectors is smaller if the data that they were produced from is more similar. For example, the distance between vectors for apple and pear is going to be a lot less than the distance between a vector for apple and a plushy tiger, because again, this is a measure of semantic similarity. And this property is essentially what enables vectors to be used to search for similar data.
Now, if that sounds an awful lot like your university math courses and you're worried that you're going to need to understand all of that math in order to be able to use vectors, let me assure you, you don't. In fact, why don't we take a look at a vector search in action with a mobile app we built. This app is going to help the end user find national parks that have some sort of attribute or attraction thereafter in their local proximity. So in this case, I'm looking for a national park that has a hiking trail with a waterfall on it. And you can see there in the app that I'm instantly getting responses of images and descriptions that are talking about hikes with waterfalls. And we can build this app with a very simple schema. In fact, there's only two tables in the application. The first table, the parks table, has all the information about the national park, what it's called, where it's located, all that good stuff. The second table is the park images. This is a table that has all of the photographs that we got from the National Parks Department, as well as social media, about all the different attributes or attractions there are in the national parks. And for each of those images, we've generated one of those vectors or sequence of numbers that Tirthankar just described. And then we can leverage those vectors to do the similarity search. So how would you generate the vectors for the images? Well, let's imagine this is the image we're working on right now. And the vector that we would generate to represent that image would contain attributes or dimensions representing the different aspects of that photo. So, for example, we pick up the fact that there's a hiking trail in the image and that there's a hiker on it, that there's a bridge over a river, what types of trees are present. All of that information will be captured as separate attributes inside that vector. Now, don't worry, you don't need to build these vectors yourself. That's all automatically done using machine learning algorithms. And in fact, the vectors that they'll produce will have hundreds, if not thousands, of these attributes or dimensions inside of them. But you get the idea about how they're going to work. So once we have the vectors, how do we do that comparison, or how do we look them up? Let's take another look at our application. Given the fact it's an Apex app, I'm able to run the same application here on my desktop. So this time I'm just going to search for waterfalls, and immediately you see the app has returned lots of photographs of waterfalls. And if you're able to see the text there, you'll realize the word waterfall doesn't appear. And the reason it doesn't appear is the beauty of vector search. If we take a closer look at my SQL statement, you'll notice there it's just standard SQL, but there is a new vector distance function in that SQL. And what that's doing is it's comparing the image vector column that we have in our parks image table to the embedding or the vector that's generated for my query input. Now, remember, my query input was the word waterfall, and somehow I'm able to compare that to image vectors. And the reason I'm able to do that is the embedding model that I've chosen is a multimodal model. What does that mean? It means that it will generate vectors for words in the same vector space that it's able to generate vectors of images. So when my query comes in saying I'm interested in finding waterfalls in the local parks, it will transform my word waterfall into a vector and be able to compare that vector or measure the distance between that vector and all the image vectors we have. And then it will return the closest images of waterfalls to us, which is what you see there in the application. Now that you kind of have an idea of what vectors are, I want to talk about how we could use them in the enterprise, because the real value of vector search comes when we can combine it with your traditional relational and other business data searches in order to solve real world problems. Now, you have a couple of ways you could do this. Option one would be to create a new vector database. There are lots of these new specialized databases on the market, each of which can do similarity search just like I showed you. And what we'd have to do in order to combine that with business data search would be we'd have to ship our business data from where it lives today over to that new vector database. Now, there are a couple of gotchas with this approach. Problem number one, what business data do I need to ship over to the new vector database? Unless you know exactly the questions the users are going to ask, the volume of business data that I'm going to need to move over there could be quite large. And that can also be a security issue if I'm moving sensitive data around in the network. It does open up additional security vector issues with that. The other issue is keeping that data both secure inside that database and also highly available. These vector databases are new to the market. They're less than 2 years old, so they don't have the same robust security and high availability that you would expect from your enterprise systems. And it's for that reason that Oracle is combining vector search into our existing Oracle database. So you can run it right alongside all your traditional business data search without exposing your data to any additional security issues and without having to move the data around. And what's great is that those vectors can be kept transactionally consistent with the rest of your business data. And more importantly, they can be kept completely secure, because all of the industry-leading security capabilities that you know and love from the Oracle database can be used right alongside with the vectors. And it's not just security that you can use with this. All of the high availability and resilient features, things like our real application clusters, parallel SQL transactions, analytics, all of those capabilities can run with AI vector search directly in the Oracle database so that you can leverage this capability in any existing or new application that you may be looking to run today.
Great. Thanks, Maria. So Maria gave you a really good tour of vector search. And frankly, this is all you need to know. She covered almost everything that you would need to know to use vector search in practice. But I'm going to walk you through another example to illustrate the point about how easy this technology is to use. So now we're going to switch to a different type of application, which in this case is a house hunting application, which basically helps the users find houses for sale that are similar to a picture that the customer uploads. So in practice, when you're trying to find a house, you need to consider both the picture or the desired picture of the house or the image of the house that you like to buy, along with other types of user preferences and business data. In this case, everybody searching for a house has a certain budget, at least I do. And everybody wants to live in a certain location, so your city preference matters. And of course, you need to also look at things like product data, what houses are actually available in the city. There's no point showing me a house in the Mediterranean that costs $30 million. Show me something in my location that is closer to my budget. And this is what is made super easy now with Oracle Database 23 and 26 AI. So first of all, house photos, the desired photo, the house that I'd like to live in, that photo is first converted into a vector and stored along with house metadata. And this is what this would look like in terms of the table schema. The house photo is stored as a blob, and the house vector is stored as a vector data type that specifies the number of dimensions and format, which are both optional. And a number of different dimension formats are supported today, including float, 32, 64, int 8, and binary. Now, we offer multiple ways to create this vector. In many cases, developers already have vectorized their data using their own libraries. So you can certainly bring your own vector embeddings. And the word, by the way, embeddings and vectors are kind of synonymous. So please substitute mentally the word vector when you see embedding and vice versa. So you can bring your own embeddings to your database, no problem. You can also use your own preferred embedding cloud service, such as OpenAI or Cohere, whatever you prefer. You can send them your data, you can get vectors back, and then you can insert them into Oracle Database. You can use libraries also in the middle tier, no problem. An exciting approach is to use a database resident embedding model, where the embedding is actually produced inside the database. So this is what it looks like. We have a vector embedding SQL function that can use an embedding model that has been imported into the database. So in this example, what you would first do is you'd first import your favorite embedding model into the database using the DBMS vector package. And you provide the location of the model and the model name and various model attributes, metadata. Once you've done that, from then on, you can generate vectors from data using that model. So it's extremely simple. In this example, you can use the model you just imported to generate vectors from your house photograph. And this SQL select returns a vector from that house photograph. Now, as Maria said, the process of finding similarity, similar images, is through simple SQL. As she said earlier, the vector distance SQL function is the only new thing required. So you can search the house table, provide the vector for the search photo, compare the vector with the existing vectors in the table, and get the top 10 matches. Very, very simple. As you can see, this is standard SQL with the new SQL function. You can become more sophisticated by combining that photo search with searches on the structured values that you need to do a proper house match. So for instance, in this example, I'm still doing the vector distance match with the existing house vectors, but I'm also filtering by the city that the customer wants the house to be in and finding houses that cost less than the customer's max budget. So again, you can see how easily you can combine vector search with much more sophisticated relational search in the same query. And this is extremely convenient for developers because unlike traditional vector databases where you have to move a bunch of data and run a subset of the searches, you can combine the full power of Oracle database relational search with vector search just in a few lines of SQL, with everything fully consistent, all data fully secure, and a full single integrated solution.
Now, everything we've spoken about thus far, we've talked about comparing your input vector to all of the vectors in the table, measuring the distance between them, and returning the top matches for your query. We call that an exhaustive search because we're really looking at every single vector in the table. And that works incredibly well as long as you only have millions or tens of millions of vectors in the table. But what if you've got a much larger data set, one with billions of vectors in it? Doing a full table scan for every query may not be the most efficient approach. And that's why Oracle has introduced new vector indexes to help improve the performance of these vector searches. There is a little gotcha with this. We do sacrifice a little bit of the search accuracy in order to get that 100x performance improvement. But I promise you, for your top K matches, you rarely notice any of that accuracy that you're losing. And you also have the ability, when you create the index, to adjust that accuracy so you can get exactly the responses you need for your applications in the time that you need them. So let's talk about these new index types. After all, the Oracle database hasn't had a new index type since 8i. So being able to get two new index types in 23 AI is pretty impressive. So the first one that we introduced was an in-memory only index. We call it a neighborhood graph vector index. It's also known as an HNSW index. In this scenario, we're going to create a graph-based index in memory. The nodes of the graph, or the circles you see there on the slide, they represent the vectors. The edges of the graph, or the white arrows between those circles, they represent the distance between the vectors. When your query comes in, we'll plot your query vector onto the graph, and then we can quickly measure the distance to the other vectors in the graph, being able to find your nearest neighbors or the nearest matches for your particular query. Now, this is incredibly efficient and very, very accurate way to do similarity search. But there are, again, some gotchas here that you need to think about. Number one, this is an in-memory only index. That means the entire index must reside in DRAM or main memory on your database server. And if your data set is incredibly large, you may not have enough memory capacity to store the entire index. The other issue can be around resilience. If for some reason you need to bring your database server down, when you start it back up again, we will have to rebuild that index into memory. And during that initial warm-up phase or the recreation of the index, your queries will have to use the full table scan until the index is ready. Alternatively, you can take advantage of our neighbor partition vector index, or IVF flat index. With this approach, this is a disk-based index, just like B-tree and bitmap indexes that you know and love today. And with this approach, what we're going to do is we're basically going to partition or group the vectors within your table based on their similarity. And for each group or partition, we will have a representative vector that represents that group. We call that the centroid. And when your query comes in, we'll compare your query vector to all of those centroids, looking for the closest top n matches for that. Once we find those closest matches, we're only going to search the partitions that they represent. So effectively eliminating any of the vectors that we know for sure are not going to be similar to your input vector, accelerating the performance by simply just not having to do that comparison. Again, as I said, this is a disk-based index. This index can be as large as you like. Most of us always have plenty of disk space on our database servers. And you can create it as a global index if the underlying table is not partitioned. But if the underlying table is partitioned, then you can create this as a local index, meaning that each partition will have its own IVF flat index created for it. Now, one of the things we've noticed, of course, with AI is how rapidly this whole area is evolving. And that is true for AI vector search inside the Oracle AI database. We are continuing to evolve it. And you see that here with each of the patch sets that we had in 23 AI, the original release that had an AI vector search. We continuously added new features and capabilities for each one of those. And we're going to continue to do that in the latest version, 26 AI. Now, I'm not going to go through all of these features for you, but I do want to highlight just two of them that I think are really useful in the indexing space. One of the real key areas that we see vector search being leveraged is to do document searches. After all businesses typically have PDF files and reports that contain very valuable business data. And to be able to search that data the traditional way using keyword search, or now using the new similarity search with AI vector search, both techniques are incredibly useful. But what if I told you we could combine both of them, do keyword search and similarity search on the same set of documents at the same time to help address your queries? And that's what a hybrid vector index does for you. When you create a hybrid vector index, under the covers, Oracle will actually create a traditional text-based index as well as the vector index. So when your query comes in, you can tell us that you're looking for documents that contain these specific keywords, but you also want documents that are talking about a particular topic. So we go back to Thanker's example of the house hunting app. We might want to say that we're looking for homes with Cape Cod architecture, but I also want homes where the description may contain a water view. Now, that could be in the description of the property, but it could also be in the images of the property. So I want to be able to access all of those homes. And that's what a hybrid vector index allows me to do. It allows me to do that combination of vector search and keyword search at the same time. Now, you do need to use a slightly different API in order to do those searches. So instead of it being the standard SQL statement that Thanker showed us earlier on, we're going to use DBMS Hybrid Vector, that new package that we've given you. You want to run the search function within that. Then you tell us the name of the index you want to use, and then whether you want to do a text search only, a vector search only, or do you want, as I have here, a union of those two searches. Then you tell us what phrase or term you want to do vector search on, what keyword searches you want to do, and then how do you want or what do you want returned from the query. So in my case, I want to see the score and also the chunk of text that contains either that keyword or is about water and views. So as I said, slightly different way to access it, but all the same power of similarity search along with keyword search. Another great improvement that we introduced was the fact that you can now have additional relational columns along with your vectors for your IVF indexes. So this means that you don't have to go back to the base table to pick up those additional columns that you may want for in the select list. And it also means that if you've got where clause predicates on those relational columns, we can filter on those columns during the index access as well. And how you create these indexes, very similar to the way you do a standard IVF index. The only difference there is the new term include. So you're going to list the include clause, and then tell me which relational or business data search columns you want added to that vector index so that we can do a simple index access and not have to go to the base table to pick up those columns.
Now, adding generative AI to AI vector search and business data search enables a completely new era of data and app productivity. So let's talk about that. Oracle Database improves generative AI by basically augmenting LLM interactions with private database content that the LLM would not otherwise have access to, that is found using a combination of data and AI vector search. This enables LLMs to use business data to produce better and far more relevant answers to end user questions while still keeping business data secure. This is called retrieval augmented generation, or RAG. So let's look at another example here. Imagine an app that helps to resolve internal support incidents for a large organization using a chatbot powered by RAG. Typically, for a large organization, when systems have issues, when people file support requests or service incidents, it's very likely that a similar issue or the same issue has been reported before or has been seen before. So if a user comes in and asks a question about a certain problem, this is the way the workflow would work. For example, if the user says, my laptop keeps rebooting, why does that happen? The first step is to take that question and encode that into a vector. Then that vector is used to search the vector database for relevant support incident documents, along potentially with additional searches that match the user's product with existing product information, plus the support tickets themselves. When this information is used to augment the prompt, so the documents on matching support incidents, plus the product information is used to build a more complete prompt that is then used to probe the LLM with. And finally, that augmented prompt is used by the LLM to produce a far more informed response than it could have done just by the vector of the question by itself, because the data the LLM used in this example included data that was private to the organization, the product information and the support ticket information. Now, what's also interesting, and this is something I tried for fun, everything I showed in the previous slide can actually potentially be done as a single SQL statement. This might look complicated, but if you look at the breakdown, it's actually very simple. The first step, again, is to generate that questions vector using a SQL function, vector embedding. Then you take that vector and you find the matching documents using vector search using another SQL statement. Then you take the results of that SQL statement and you compose the LLM prompt, again using SQL. You take all the documents that were retrieved and you concatenate them essentially into an LLM prompt and then run that SQL statement. And then what you can also do in Oracle Database is you can also call the LLM directly from the database using another PL/SQL function in this example that will retrieve the LLM response using SQL. So this is a unique capability where you can combine vector search, prompt construction, LLM interactions all inside the same SQL statement. Very, very, compact representation of what could be several hundred lines of programmatic code.
That's super impressive to Thanker. And the Oracle AI database can go beyond just RAG because we can also work with AI agents. Now, if you're not familiar with agents, what they are is more a dynamic multi-step workflow where the agent can perceive its environment, it can process information, and then make decisions based off of that, all to achieve a particular user's task or goal. Now, typically you build agents using frameworks today, whether you want to leverage the open source frameworks like LangGraph, or you're using a proprietary choice such as our Oracle's OCI agent service or Amazon Bedrock, wherever framework you choose to use to build your agents, Oracle offers extensions and handlers to help integrate the database as a data provider and a vector search engine to those frameworks. And why would you want an agent rather than just using RAG, as Tafanka described? Well, there are certain questions or tasks that we're going to ask AI to do that RAG just can't quite solve for us with going to the LLM just once by using what we call one-shot RAG. So in this example, the mobile app that you're looking at is Benny Benefits. This is an internal app that our organization uses to help the employees be able to understand the benefits that they get from their health plans. And in this case, our user Jane has asked the question, does my plan include braces? And if so, how much is my deductible? If we were to do this with one-shot RAG, it's possible that we could overwhelm the LLM with too many details about all the different benefit plans that our organization offers, and it could answer the question incorrectly. In this example, telling Jane that her vision plan covers braces when, of course, we know that's not the case. So how would things differ if we were to build Benny Benefits as an agentic AI workflow instead of one-shot RAG? Well, the first thing that's going to happen if we go with this approach is that rather than sending Jane's question directly to the LLM along with additional context to get a response, we're actually going to ask the LLM, what information would you need in order to be able to answer Jane's question? And the response we get back is 3 key pieces of information are needed to answer that question. First and foremost, we need to know what plans Jane has subscribed to. Then, once we have those plans, we need to see if any of those plans cover braces. And if they do, we need to be able to determine what the deductible should be. So let's step through what this workflow would look like. We start by trying to address part 1 or question A in our workflow. And we're able to find out what plans Jane has subscribed to by doing a simple relational query on our HR database. We can extract out all of the benefit plans Jane has subscribed to. Next, we want to be able to see if any of those plans cover braces, and we can do a vector search on those documents to find documents that are related to braces. Once we're able to reduce the number of plans that we're sending to the LLM, we can send that more curated list of benefit plans along with our question, which is, do any of these plans cover braces, to the LLM. Depending on the LLM's response, we can take 2 different actions. If the LLM comes back and says, no, none of Jane's plans cover braces, then we can have the application tell Jane, sorry, your plans do not cover braces. If, on the other hand, the LLM comes back and says, yes, I have found Jane's dental plan covers braces, we then need to find out what Jane's deductible is. And in this case, we'll send her dental plan along with that additional question, what is the deductible, back to the LLM. And based on its response, we can formulate our response to Jane that says, yes, your dental plan covers braces and your deductible is $200. That's basically what an agentic flow looks like. And Oracle is working hard to allow you to have the full agentic AI workflow run natively inside the Oracle database. You know we already have vector search, but we've also added annotations to help give the LLM additional context about the data it needs to give better answers. We're also doing built-in agent frameworks in the Oracle database. So we've got the private AI data agent factory along with select AI agents coming in the Oracle database. And of course, Oracle now has its own MCP server. But rather than listening to me describe it, I'm going to hand you over to Thankar, who's going to take you through some of these new components.
So Oracle SQLcl is the modernized version of SQL Plus. It's a command line that is very popular. And this is now an MCP server, which means that any SQL or SQLcl command can be invoked by a large language model like Claude via any client like Claude Desktop. So in this example, you can see in Claude Desktop, you can basically just chat with the database. This is a very simple interaction here, saying list the available connections. It uses the SQLcl commands to figure out what connections are currently active in the database. So it basically brings the full power of the database to Claude, and Claude can then interact with it just like an end user. Now, there is an interesting sort of caveat to this. Enabling this essentially allows LLMs to become, for want of a better word, like a human data analyst, which is great, except that even human beings don't do really well without good documentation, clear explanations for what they have to analyze. So if LLMs have to infer the intent and the semantics of data from cryptic table and column names, this becomes problematic. If you give an LLM, or a human being for that matter, a table that looks like this, XYZ with columns C1 through C4, and you ask a question like, write a SQL query that will tell me what the average employee salary is in each department, I wouldn't know how to do it, and neither would a large language model. So the cryptic schema names, which are very common in the industry, unfortunately, are problematic. Now, what we have done in 23 AI and 26 AI now, and what we have backported to 19C as well, is a new concept called annotations, which basically are designed to help to explain data and the semantics of data to AI. So if you have a table whose definition looks like this, and that schema could be part of a packaged application, so you really can't change the schema names, you can augment those definitions with annotations that provide much better clarity on what the data actually means. For instance, you could say that XYZ really is meant to store employee details, and the column C1 is meant to store salary, and C2 is supposed to store the name, and C3 stores the department, etc. So you can basically add documentation on the intended use of that data. And once you do that, then the LLM can actually run reasonable reports on that data. As in this example, it now knows that this table is the table of employees, and these are the columns for salary and department. So it can actually give you something meaningful. So this is very, very important at the age of AI to explain data and semantics to AI. We have a tool through SQL Developer, which is very popular developers, a workflow tool to enable adding AI enrichment for metadata. So if you have a large schema, it's going to be work because you have to go through the tables, but SQL Developer's workflow makes it simpler. It helps break it down by the least annotated tables, encourages annotations being added to those tables and columns, and provides the ability to also use AI in turn to generate these annotations. And as you add annotations, it reports continuously on the number of tables that have been thus enriched. It will tell you how far you've gotten and how many have left to go. But it is a prioritized list, so it uses the tables in an order that it thinks makes the most sense, because those are the most relevant tables for the application based on access patterns. In addition, we have a lot of other great things that are imminent with Oracle database, AI capabilities. Maria talked a lot about our agentic features and plans. We are about to release very soon a private AI agent factory, which is essentially a no-code platform, extremely simple to use, simple drag and drop, and you can edit some of the prompt description in each box, and you can compose very sophisticated agents with this. This will include some pre-built agents that you can further compose and create more complex agents from. And you can compose them in arbitrary ways to create very sophisticated workflows. And you can also build your own primitive building blocks and compose them. It's extremely flexible and very powerful because it's a no-code way to create these extremely sophisticated workflows. And all agents essentially can use Oracle Database AI features, and this enables developers to rapidly roll out smart assistants. Another requirement that comes up from our mission-critical customers is, in many cases, customers, especially financial services and many governments, have very sensitive databases which cannot share data with public large language models. So the agentic workflows and RAG that are often required for AI can't involve a third-party LLM. They can't use third-party embedding services to make vectors from data. So we are providing an AI services container that lets customers who wish keep private data private. This will include open-weight large language models, a number of vector embedding models, and other AI services such as NERs and re-ranking models, and other machine learning models. Now, this container runs wherever the customer chooses. It can be deployed on premises along with the customer's database. It can be deployed on the customer's private cloud, or even on public cloud within their own tenancy. So full freedom to deploy, but the main point is that this data stays with the customer. There is no third party that is receiving the information to vectorize or the prompts to use for retrieval augmented generation. We are also delivering, again shortly, an autonomous vector database cloud service. Now, we already have a very sophisticated, full-featured autonomous database that has vector support. The difference is this is purpose-built and is a subset of the autonomous database designed to really work for AI developers and data scientists who may not need the full power of everything Oracle Database has, but really requires certain specific features like vector search, like vector embedding generation, and like RAG workflows. So here, Oracle Database is used as the underlying vector store. This is designed to be price competitive with leading dedicated vector databases. This advocates an API-first approach. It will support SQL, but we would recommend that data science developers that are used to using API-based vector services, vector databases, can use the APIs we provide for programmatic vector application development. Of course, this is built on autonomous database, so it is mission critical, highly available, highly scalable, and completely secure because it's built on the bedrock of a very, very advanced database engine. And if after you try out vector database, autonomous vector database, you feel you need more functionality, you can then convert that database with a single click into a fully featured Oracle Autonomous Database, because that's what it is under the covers. And you can expand your functionality easily by just pushing a button and saying, look, I want full ADB. So that's the beauty of the vector service delivered as a specialized service, but fully leveraging the converged infrastructure that underlies Autonomous Database. We have other applications of vector search we are trying to provide with the database. This is coming soon again. This is called Trusted Answer Search. It'll be a free tool that will basically map an end user question to one of a number of reports without using a large language model. This is based purely on vector search. Again, the end user question is transformed into a vector, and the vector search is used to find the closest matching report based on its description vector. This also includes a workflow. So if I match the wrong report, I can provide feedback saying, I'm sorry, I wanted a different report. The administrator can then add the fact that this was an incorrect match so that future questions that are similar will then match the correct report. This tries to not use LLMs that are used for more unbounded data exploration, because here we're exploring within a finite set of reports. But you can certainly use LLMs to generate the reports, to limit the content within reports, to generate descriptions, but to not directly provide the answer, because vector search is the right technology here to provide a match within a bounded set of choices.
So there are a lot of very exciting new capabilities coming with Oracle AI Database 26 AI and those additional tools Tefanker has shared with you. I just want to do a very quick recap at the end of our session here to remind you of what we talked about and how Oracle is now a vector database. We've embedded enterprise-grade similarity search right into Oracle's converged data architecture, allowing you to seamlessly combine it with all of your existing business data search. We also have capabilities to help you leverage all of the data that you've got inside your existing databases to be able to provide additional context when you build agents for your users, whether that's chatbots that they can interact with or other AI-driven agents, so that you can provide additional context to large language models to allow them to be able to answer your users' questions, but keeping your data secure. We also want to ensure that any system that you're building with similarity search or as the backend engine for an agent or a RAG scenario has all the full mission critical capabilities, reliability, and more importantly, scalability that you know and love from the Oracle database today. Everything that we've spoken about today is available for you to try out yourself at home. You can try it using our free hands-on training using the Oracle AI Vector Search Live Lab. You can watch videos on how to build your own RAG agents, or you can check out all the additional technical information that we share over there on our blog so that you can always keep up to date with all the latest and greatest comings that we have for AI vector search. But with that, I want to thank you all for your time today and for joining us. Hope you found the session useful.